flow past immersed bodies. So this is in fifth module of our fluid mechanics subjects, in which part of the topic is flow past immersed bodies. So in this we are going to study about the bodies which are under different forces applied by the fluid, which is under which it is flowing or the movement is there. So example, if you take, there are many examples which you come across the regular days. So like vehicles you can take, wind turbines you can take, or ships you can take, or propellers you can take, automobiles you can take, or the different jet planes or the parachute you can consider. In all such bodies which are in movement with air or in the liquid are going to exert or achieve or feel some forces. So those forces we are going to study in this chapter. So in all bodies, if you consider in environment which are either in movement with air or in the liquid or in the gases also. So keeping this in mind, we'll discuss about the different forces. So for this we need to assume, for the experimental purpose, so either the body is in motion when the fluid is in stagnant, or sometimes the body may be in motion and assuming the fluid is in stagnant. So in such conditions we are going to experiment and we are going to find out some different forces or the coefficient of different forces in different directions and other things. So here in this chapter we are going to assume the body is always in a stagnant condition and the air is moving with a given velocity. So by this we are going to assume and we are going to derive some equations, small equations, very small equations. Then we are going to use the numericals. And in the numericals, maybe the body is moving, or else vice versa, the air is moving, or the liquid water is moving. In such cases, we are going to consider the same equation with the same velocity. So velocity will be either for the body or for the fluid. Okay. So now we will consider the first part is forces on the stationary body by flowing fluid. So here if you consider the flowing fluid, so for that fluid we are considered velocity u, at which the fluid, maybe gas, liquid or air, is moving or approaching the any body. So that body we are considered here with a aerofoil shape. Why? Because many times if you consider, the bodies are either circular or smooth aerofoil shapes, like plain body or the blades or the wings we can call. So those all bodies are in the aerofoil shape. And nowadays if you see the vehicles also, the front shape of the vehicles or the body design of the vehicles, if you see, many times nowadays are designed with the aerofoil shapes. But earlier days if you consider the truck or the bus shapes, which are completely flat bodies, which are also called as bluff bodies. So in that situation we have to consider the aerofoil shape as a general case to discuss about the forces. Now as this air approaches for a given entire aerofoil shape, so as usual for derivations we have considered a small area, and later we are going to integrate the small area into the full area to resolve into different forces. So similarly here also we have considered a small area called as dA. So that small area is shown at the tip of this aerofoil shape. So that area is dA shown here. Now the forces which are acting because of the air flow, we can write it as, one is the pressure force or the force acting on the surface of this body, that is written as P into dA, that is pressure into dA. It is nothing but the force, or it is also called as pressure force at a given horizontal angle theta. So theta is the angle between air movement as well as this pressure force. And next is the shear force. So due to this inclined small area, there is a shear force exerted, that is given by tau naught into dA. So these two forces are the major forces which are acting on the inclined surfaces. So the inclined surface may be in this shape or in the opposite shape, or it may be horizontal, vertical, in any given angles that you can assume. Next is, for a full body, if you integrate later, we are going to resolve the forces into two main categories. That is, one is in horizontal direction, drag force. One more is in lift force in the vertical upward direction. So due to this lift force only, these bodies in the air or in the fluid are going to be balanced. So to balance these all different shape of bodies, we are going to discuss about the lift force and the drag force by which the vehicles or the submarines or the boats are going to float in the different fluids. Or you have to reduce the drag force such that the lift force should be more. And for vehicles especially, the lift force should be not more than the weight of the body itself. Otherwise it may float. So we have to reduce that lift force as well as the drag force should be less, so that efficiency of the moving vehicles will be more, or the power required to maintain those bodies, to maintain the different velocities, will be less. So keeping this in mind, the forces after resolution for the full aerofoil shape, if you see, the horizontal direction, the resistance, what is going to be there, that force we are going to call it as drag force, which is denoted by F with the suffix D. The lift force, due to which the bodies are floating in the air, like aeroplane, with the help of wings of aeroplane, the aeroplane is floating in the air. So that lifting force is FL. So for the floating bodies, FL should be high, then the FD is in a general case. And the resultant force, as you know, all of you, in 2 dimension, if you see, we can resolve into 2 forces like FL, FD. If you take in a vertical and horizontal direction, the resultant force can be also found out. Now coming to the components in the direction of motion, if you see, this is called as the drag force or the resistance of the body. Means whenever the air is moving opposing the bodies, so that force is called as resistance force or the drag force. And whenever the power is required to overcome this drag, so that power we have to calculate what is the required to maintain the body in a given moment. So that is also can be found out by using this drag force. So these things we have to keep in mind for the calculation part. Now to understand the components, how to resolve and how to find out the total or the resultant forces. So for that we have taken the resolution of forces. So before that we can observe component of total force or the resultant force is perpendicular direction of fluid motion is called as lift. So that is denoted here FL in the above sketch. And lift is the 0 for the symmetrical bodies. If the body is symmetrical, for those such conditions, the lift force will be almost 0, which is not possible to achieve. And for different bodies, for asymmetrical or any other shapes of the aerofoil shapes or the uneven shape, for a given symmetry of the body, if you consider, if it is uneven shape, then you can have the lift force. So lift is almost equal to overcome the weight. So this aerofoil shape, if you see, it is not symmetrical. And at the bottom side, if you see, it is about to take the air pressure or the resistance due to the air, and it can float above in the vertical direction rather than coming to downside direction. So to come to the downside direction, I can rotate this aerofoil shape in the downside direction, so that whatever the air pressure is coming and hitting the blades, it will try to take it downside. So like this aerofoil shape of the wings of aeroplane can work in lifting the body or taking down to the earth. So like this we can discuss later in the examples. Now coming to the expression, how to find out the resultant force. So for that, first assuming the small area dA and pressure force acting on the small area, that is PdA, and shear force tau naught dA, which is shown in the uppercase sketch, and theta is the angle made by force PdA with the horizontal or the air movement. So in this case, if you see the small area we have shown in the both sketches here to resolve the forces in both horizontal and vertical conditions. So first case, what I have done in first sketch, dA area is taken. In this, whatever the pressure force is acting, only that is resolved in vertical direction, that is PdA sin theta. According to this theta, if you consider the vertical downside direction because of the pressure force of air is PdA sin theta, and the adjacent horizontal axis, if you see, that can be resolved as PdA cos theta. So everyone has observed these conditions in many mechanics subjects. So in similarly in fluid mechanics also, we are going to resolve the forces like this. Then the second sketch, if you observe, again small area dA in the same case of aerofoil shape, what you have considered is taken. So theta is considered here as per the given sketch, or after tilting the body and other things with the tangential force. So that after resolving this tangential force tau naught dA in vertical direction, so it is upward direction, that is tau naught dA cos theta, and at the horizontal axis, if you see in the x direction, that is tau naught dA sine theta. So like this we can resolve the forces and we can write the resultant forces. So before going to the resultant force, we should know the lift force and drag force. Now you can observe, once we resolve these two forces in a different horizontal and vertical components, now I can write the drag force, which is always in the horizontal direction. So that drag force, I can write it as, considering two horizontal parameters, that is p dA cos theta plus tau naught dA sin theta. So those two are in the horizontal direction, so I can add those two and I can call it as drag force. Similarly, I can integrate. Why we are integrating? Because as earlier I have told you, for an entire body we are going to consider from small area to the full body. So for full body we have to integrate all the small components. So for that we have integrated here and we are writing FD. That is the total drag force. That is integration of pressure force in horizontal direction, then shear force in the horizontal direction. So that becomes integration of p dA cos theta plus integration of tau naught dA sin theta. So that I can call it as one equation for FD. Now here, before going to the lift force, first we'll discuss the drag force, how it is going to act and how it is going to behave. Because this is the major force which is going to be acting in either 3-dimensional, 2-dimensional, or various types of drag force are also available, due to which the body lift is going to be dependent. Now coming to the total drag or the profile drag force, if you see, this can be written as pressure drag plus friction drag. Nothing but what we have found out now, the pressure force and the shear force. So if you add both those things, it becomes profile drag, or is also called as form drag plus skin friction drag. So this will discuss by the below sketch. Now coming to the first one, skin friction drag on flat plate. So this, if you observe, the flat plate what you have taken, either it is in vertical position, one is in horizontal position. Now coming to the vertical position, if you see, if the angle is 90 degree, means it is exactly normal to the air flow or the resistance to the air. If you consider, whatever the air movement is coming and hitting this plate is going to have the wakes at the backside. Wakes are nothing but the disturbance in the air movement, and it is going to prepare low pressure zone at the backside. Means it is not going to support this body to resist the air movement. So this type of bodies, always which is having more resistance to the air movement, those bodies we are calling it as bluff bodies. And the bodies which are having the very less resistance, like theta, when theta is 0 or the plate is kept in horizontal direction, resistance of air will be very less. So in that condition, we are going to call it as a smooth body or a flat bodies. Now in such a vertical plate condition, if theta is 90 degree, in such case, if you see, the pressure drag force will be maximum, that is nothing but p dA. And the shear force, if you see in the vertical directions, that shear force will be very less compared to the pressure drag. So that pressure drag force will be maximum whenever you keep the body flat or facing towards the normal to the air, like a truck or bus body. Now next is, again, wakes for the different aerofoil shapes. If you see, for a car, if you see, in the front side the bonnet is inclined towards the ground, such that it is always trying to keep the body on the ground, not to lift the above the body above the ground. So like that, if the aerofoil shape of the wings of the aeroplane, if you see, that can be tilted in any direction to lift and keep down to the ground. So like this we can discuss in the flat surfaces. So at the bottom I have discussed about the plate which is kept in horizontal direction, where theta is written 0 here. In this, the pressure force is acting on the tip of the plate, which is very negligible because of the plate thickness. But the surface of the plate, if you see, either on the top or the bottom, there is some friction. So that's what, to reduce the friction, the body should be very smooth. So that due to friction force of the plate, some boundary layer or the air force or the flow of the air is going to reduce. So that layer is shown here, boundary layer profile. Means at the tip, the velocity of the air is equal to the velocity of the air which is coming before the plate, and after that the velocity of the air is going to be reduced, such that the friction force or the resistance force of this plate or the shear force is going to be increasing in the order. So in these two cases, what I'm going to tell you is, if the body is completely flat, 90 degree facing towards the air movement, then only the pressure drag force will be maximum. And if the theta is 0 or else the plate is kept in horizontal direction, then friction force or the shear force is maximum for the given bodies. So like this, drag forces are going to be acting on the bodies. So always we have to try to keep the bodies in horizontal directions to reduce the drag forces and to increase the lift forces. And these conditions will change depending upon the different bodies. I hope this is understood. Now we'll come to the lift force. So at the bottom, if you see, lift force is due to the pressure in normal direction as we discussed earlier. So that is given by dFL for a small body or small area. So here we are discussing only two-dimensional forces in the two-dimensional resolution, but actually in the real cases, if you see, we have to analyze for the three-dimensional drag forces and lift forces. Everything we have to keep in mind and we have to solve the problems. But in the syllabus, we have only for the two-dimensional cases. So that is given by, now lift force, if you see, as in the resolution of forces, here if you see, we have shown in the vertical direction, FL. So in the vertical direction, which all forces are there, that we are going to add. And before going to add them, we have to just observe the PDA sin theta in vertical direction. If you see, it is in the downside direction, and shear force which is acting in the vertical upside direction, tau naught dA cos theta. So it should be a difference of both the forces. So that is written here. dFL is, for a full body, I have written here integration of PDA sin theta minus of integration tau naught dA cos theta, or vice versa. Depends on the magnitude. So similarly, resultant or total force can be given, as you know in the mechanics, square root of summation of drag force square plus lift force square. And if the pressure and shear force details are not known, so until now we have discussed about the pressure force, shear force, okay, and different sin theta, cos theta components examples. But here in such cases, if these conditions are not given, in that case we are going to use the coefficients and with the simple formulas. So those formulas are nothing but, these are the direct formulas without derivations in syllabus. So that you can just observe here. Drag force can be written as CD A rho U square by 2 or V square by 2 is nothing but CD is the coefficient of drag, area is the surface which is in contact with the air or fluid or liquid, rho is the density of the air or the fluid you can call, U square or the V square, generally we take V square. So that is nothing but the velocity of the air if air is moving. If body is moving, V square is the velocity of body itself. So this you have to keep in mind. Similarly, for the lift force, we can write it as coefficient of lift CL into area of the surface is in contact. Similarly, density of the fluid, velocity of the fluid or body by 2. So these two formulas are very important for our numerical examples. Similarly, to keep the bodies in movement or to control the balance of the bodies, we also need to have some power. How much power is required to maintain this body in movement or to lift the bodies in given positions. So that can be also found out by just multiplying the force into velocity. So by this we are going to find the answer in watts. So by that we can multiply drag force and velocity, by which we can consider the power required to maintain the body at a given positions. Now next is, in some cases if the angle is not given and we need to find out the angle also. In such cases we can take tan theta equal to ratio of FL and FD if you take by this resolution of forces also. Here you can see the resolved forces. From this if you see FL and FD are there. So by that ratio if you take FL by FD is nothing but the tan theta. So theta can be found out if the angle of inclination is required, or in different examples we may find out the forces of drag, lift, or else in the some conditions we need to find out the coefficient of drag or coefficient of lift, or some cases we need to find out the area required or the velocity to be maintained with given all details. So like this you can substitute any number and you can find out the unknown values. So lastly we'll discuss about the different drag forces in 3 dimensions. If the conditions are in 3 dimensions, which is not in syllabus, just we'll see. So earlier we have discussed the pressure drag and skin friction drag or the shear drag. Apart from this we have the profile drag. So the profile drag is what? the sum of skin and pressure drag, that is called as profile drag, that we have seen in the drag force while writing the equation. That is nothing but the profile drag. Next is wave drag. So this is initiated because of the movement of the air, that is called as shock waves in atmosphere, or else in submarines or the boats or the ships, if you see, the liquid is continuously moving in the water, or the some waves are generated. Those waves are also applying some drag on the body, so that is called as wave drag. Next is induced drag. So this is nothing but the other than two-dimensional forces what you have discussed now. Other than this, any three-dimensional forces are also coming into picture, which are inducing some other forces or changing the intensity of the two-dimensional drags. That also you need to consider. So that is nothing but drag due to three-dimensional nature of flow with finite length of body. So for a given length of body or area of the body, how much is the induced drag is there for in three-dimensional objects. Then last drag is deformation drag. This is nothing but especially in the air movement or in the compressible flows, if you see, continuously the air density is going to change. So similarly here also, resistance experienced due to the widespread deformation of the fluid particle itself. So here what I am telling is the drag force because of deformation is nothing but the deformation of the fluid or the air or the gas. So whenever that gas or air is going to deform, so that drag force which is intensifying the forces on the body because of the change in the compressibility, that is going to resist the body. That also we have to consider in three-dimensional analysis. So that is, I will read once again, resistance experienced due to the widespread deformation of the fluid particles. So that force or the drag we are call it as drag due to deformation of fluids. Okay, now this is all about the theory in flow past immersed bodies. Now we will take some simple examples to understand how to solve the problems and what all things we need to find out. So one such example is, first one I'll read, a flat plate of 2 meter by 2 meter moves at 15 meter per second in air of specific weight 11.28 Newton per meter cube. If CD or the coefficient of drag is given 0.15 and coefficient of lift is also given 0.75, determine the drag force, the lift force, resultant force, power required to keep the plate in motion. So what we have discussed, they are asking here. Last one, calculate the direction of resultant force. So these all things like what theory we have discussed in the same fashion, in the same process, they are asking the questions. Now in the solution you can observe, I have not written the given data, already it is given in the question. So first coming to the drag force equation we already know. So that is a CD A rho V square by 2 or U square by 2. So in this case you can observe here, coefficient of drag is given 0.15. So drag force is less than lift. Okay. And area of the plate is also given 2 by 2 meters. Then rho is given in terms of what? Specific weight. So that we need to consider in density. So for density to convert from specific weight, we have to divide by 9.81. So that will give us the force drag in newtons. And velocity is also given 15. So once you substitute all these in equation, I can note down the drag force is 77.61 newtons. Similarly, lift force, only by changing the coefficient of lift in the equation, I can find out the lift force, that is 388.07 newton. So here coefficients are also maybe high or less, but the forces, if you see, the lift force is also higher than the drag force, means the body is going to be lifted. Then resultant force you can find out, that is 395.76 newton. Power required, so here drag force we are taking. So drag force is how much? 77.61 into the velocity of the body, that is 15. So that will give us 1.164 kilowatt something. Then direction of resultant force. So here comes the point. So here we need to find out what is the angle of the body or the angle of the flat plate to be maintained, or the direction of the result force which is acting, that is theta is equal to tan inverse of FL by FD. So by that you can find out the angle is 78°.69. So this you can do by using calculator, and just note down all the given data separately and do it by calculator. So you will get some numbers. If any changes, just note down and keep it. Okay. Next example with the application we'll take. A truck is traveling at a speed of 85 km per hour. So just assume one truck is moving with a velocity. Air is assumed as stagnant. Has a total resistance of 19,620 Newton on a projected area of 6.5 meter square area. Of the total resistance, 30% resistance is due to rolling friction. Just note down here the wordings. Of the total resistance, 30% resistance is due to rolling friction and surface friction. Remaining resistance is due to form drag. So you have to recall all these wordings. Form drag is nothing but the pressure drag itself. Calculate coefficient of drag if the specific weight of air is 12.27 Newton per meter cube. So keeping these all given data and what we found out, we'll just convert some data and we'll just see the solution. Now here in this problem, speed of the truck is given 85 km per hour. So to convert this in meter per second, because we need velocity. So this you already know, I have converted here. It comes under 23.61 meter per second is the velocity of the truck which is moving. That we need to consider in formula. Now total resistance given is 19,620 Newton. In this resistance, the resistance due to rolling and surface friction, okay, that is given 19,620 Newton. Apart from this, 30% of the force is due to rolling and friction, that is considered as 0.3 or the 30% is under 5,886 Newtons. So this is the difference what we need to take for the drag force now. So drag force is nothing but total resistance minus the surface friction or the shear friction or the shear force is nothing but what? The pressure force, what is the resistance form drag minus the shear force. I hope you are getting this. This we have done in the derivation is nothing but PdA minus tau naught dA. So in such case, we have taken the difference of these two forces to find the drag force, that is 13,734 Newtons. So just check the values. Then here in the calculation they are asking only the coefficient of drag. Lift is not asked. So we are going to find out only drag force by using the coefficient of drag. Area is also given, which is in contact with air. Density is given indirectly like earlier problem, and velocity of the truck is also given. So CD value is coming around 6.07. So because of this CD value 6.07, if we maintain with the flat body, we can run the truck at 23.61 meter per second, or else we can maintain the force of 13,734 on the plate. Or else you can change the values and you can run the truck in different speeds. That is the meaning. Next problem, another 2-3 problems and we will end up. A man weighing 981 Newton descends or come down to the ground from an aeroplane with the help of parachute against the resistance of air. So by this you can understand there is a buoyancy force or the resistance force or the drag force or the lift force which is opposing the person to come down because of the parachute. And we are going to consider the parachute area here because that is larger than the human cross-section area. The shape of the parachute being hemispherical of 2 meter diameter, so that's why they have given the cross-section area of the hemispherical parachute. Why they are telling hemispherical? Because we need to consider the area on the basis of the standard geometry. So for that he is telling hemispherical, that parachute 2 meters in diameter. So here we need to find the velocity of the parachute with which it comes down, and for CD value 0.5, nothing but the coefficient of drag. Then density of the air is given 0.00125 gram per cc. This we need to convert. Then they have given the viscosity, that is 0.015 Stokes. So which viscosity we have already discussed in the first chapter, so that you can recall again. Now these all data whatever is given, which is only required for the problem, we need to consider, because if viscosity is required or the density is required or the velocity is required, then you can go for the Reynolds number also. By the Reynolds number one can find out whether the laminar flow is there or the turbulent flow is there, or for that condition what is the CD value you can find out. So these all conditions will be given in the other problems. Now in this problem if you see, density we are going to convert in kg per meter cube. So conversion is given here, means what we are doing, we are converting that cc into meter cube first. So that is 10 raised to 6 we are going to multiply. Then grams we are going to convert it into kg. So by that we are going to divide by 1000. So like this we are going to convert in kg per meter cube. Next is same process. We need to find out here drag force, and finally we need to answer for the velocity at which it is coming down. So drag force is given is nothing but what? So drag force is always acting in the downside direction or the horizontal direction. So in such cases, if you see, the drag force itself can be considered as the weight of the human body itself, that is 981 newtons. So 981 newtons is considered as the drag force which is dragging the parachute downside. With CD value is given, area is given, then everything is converted. So if you find out, V will come out to be 31.61 meter per second. That is the velocity at which parachute is coming down. Next problem, just I'll tell the fundamentals here, how to be solved here. So kite is weighing 11 Newton. Again, this is the weight of the kite. That itself you can consider as a FD again. Next, an effective area 0.9 meter square is also given. Tension in the kite. So to pull down the kite at a given directions, we have the string here. He is also pulling in downside direction at 33 Newton. So angle is not given, or given, we'll see. When the string makes an angle of 45 degree with the horizontal, this is very important. String is making 45 degree with the horizontal surface. For a wind velocity of 9 meter per second is given. Determine the coefficient of drag and lift. Specific weight of the air is 12.25 Newton per meter cube. Kite assumes 8 degree angle with the horizontal. So these all things are very important, because kite itself is, we are going to consider it as a surface or a small area which is inclined at 8 degrees. According to this inclination, if you see, the kite is going to be lifted up. If the kite is below 8 degree, if it is turned, then it is going to come down to the downside direction. So like this, we have to just assume some analysis whether it is going to be floating above or coming down according to the given position. So after conversions, the component of the pull along the FD means what? The drag force, if you find out the given component as the resolution of forces 33 Newton force is given. So in the drag direction or the horizontal direction, if you resolve it, the force is around 23.33 Newton. That is nothing but the drag force. Then lift force is in the vertical direction upside. If you see, it has to overcome the load as well as it has to lift the body. So in such condition, they have taken the resolution of the force in vertical upward direction, that is 33 sin 45 plus weight of the body. So that will come around lift force 34.33 newtons. So by these two forces, drag force and lift force, we are going to inversely finding the coefficient of drag and coefficient of lift as written here, 2fd by a rho v square. So once you substitute these values, one can find out CD and CL values. The last problem, we will end up the topic here. This is very interesting and more understanding way. A jet plane which weighs, weight of the jet is given here 29,430 Newton, and having a wing area of 20 meter square. See here, now in this problem also, the body of the aeroplane they have almost neglected, but the wing area they are going to consider. Why? Because the wing itself is going to decide whether the body is going to be lifted or inclined towards the earth. So this is more important than the body of the aeroplane in the floating bodies. So wing area is 20 meters square, which is in the contact with more amount of air, flies at a velocity of 950 km per hour. This you can convert. When the engine delivers 750 kilowatts, so now power is given, 65% of this power is used to overcome the drag resistance of the wing. Okay, so it is related with the drag force, which is the 65%. Calculate the coefficient of lift and drag for the wing for given specific weight of the air is 11.87 Newton per meter cube. Now speed I have converted in meter per second, that is 263.88 meter per second. Conversion is already given earlier pages. Power used to overcome drag resistance. So here you can observe what power is used to overcome the drag resistance. That is 65% of the power delivered by the engine. Means 65% of the power is only lost to overcome the drag. You have to understand. So once this drag force is overcome, then we can find out whatever is the power required to maintain that body in a given floating condition. So that is 60.65 into 750. That is 487.5 kilowatt is only used to run the body. Remaining all force is only wasted in the overcoming the drag. Then density you can find out 1.203 kg per meter cube. Now comes to the point, power required to overcome drag resistance. So that is nothing but FD into V, nothing but the power to maintain the body. This we can equate with the force required to maintain the body at a floating condition into 1000. So 1000 why I have multiplied here, because it is in kilowatt. So both the powers now we are equating, nothing but the power required to maintain the body in floating condition, that is 487.5 into 1000 watts, is nothing but equal to, as per our concept what you have discussed, force due to drag into velocity. So that I can consider, and I can find out what is the total drag force which is acting on the body, not because of power which is overcoming the drag force and moving in the forward direction. That is nothing but different. Here we are talking about the drag force which is possible or which is emerging from the body. That force coming to be 1847.43 newtons. This is due to the wing body. And CD you can find out by the formula, that is coming around 0.0022. Just check by calculators. Then lastly we need to find out the coefficient due to lift. So again coefficient due to lift is force we cannot find out because force is also not given, CL is also not given. So here weight of the body itself is given in the vertical direction, which is moving downside, that should be lifted up. So taking that weight itself, weight of the jet plane itself as a force due to lifting force as 29,430 Newton, one can solve for the CL or the coefficient of lift, that is coming around 0.0351 newtons. Sorry, 0.0351 dimensionless number. So this equation is nothing but CL is equal to what you have seen in the earlier topic. You can see here how we are finding the CD and CL by using the FD equation itself. So that is given by 2FL A into rho V square. So by using this formula itself, we are finding the CL as, or the coefficient of lift as 0.0351. Okay. So I hope this is covered everything, like theory, some equations, how the equations we have arrived, how to resolve the forces in all in 2 dimensions. We are not considered here in the 3-dimensional bodies. And these numericals are just using the equations, simple equations or the formulas from the same theory. And we are going to just assume the some components or the lift and drag forces, and by that we are going to solve the different forces. Okay. So in same fashion, different types of bodies will be given, like jet plane, submarine can be given, ship can be given, or bus can be given, truck can be given, like different kite is there. Different types of numericals will be available, but the main funda is to how to use these equations and implement in the proper dimensions or the units. Then you have to solve for the given values. Okay. Thank you everyone.